Use Newton's second law analysis combined with torque to solve the following problem as shown to the right. A uniform horizontal 15 Newton beam. All right, they're talking about the weight. So instead of giving us mass in kilograms, we're giving us a weight in newtons, which is fine, Might even be convenient. That's 2.5 meters long, attached to a wall by a pin hinge, allowing it to rotate. Far end of the beam is supported by a steel cable that makes an angle of 50 degrees. Theta with the horizontal. Squirrel weighs 2.5 newtons and stands 0.5 meters from the wall. System is in static equilibrium. Okay, so we're going to draw an extended free body diagram of the hinged beam. So I have no idea what an extended free body diagram is, so I'm just going to draw a free body diagram, and hopefully the two are similar. So even though I know we have a picture on the right over there, I'm going to draw my own picture just because it's kind of nice. It helps me kind of visualize what's going on. So we have various forces here. We have our force due to the beam, which is just the weight of the beam, weight being the force that's related to gravity and mass. We have force of the squirrel going down. We have force tension going up. Some people just write T. I write force with a subscript T. It's fine. Same idea. And the idea here is we have force squirrel, force beam going this way, force tension going up that way, and it's allowed to pivot along this at that point right there. So we're going to use two ideas here. Well, one idea viewed in two different ways. We're going to say the sum of all forces, and that's just going to look at the y direction, the up and down, equals 0, because it's not moving, it's not accelerating. If it's not accelerating, the sum of all forces equals 0. Well, looking at the same concept, sum of all forces equals 0 with no acceleration, we can say the sum of all torques, which is moment of inertia times alpha. Since there is no rotation, there's no angular acceleration, which means there is no, the sum of all torques is 0. So then I'm just going to start writing these out, and we'll kind of see where it goes from there. Hopefully it goes somewhere good. So we have force, torque in the y direction, minus force squirrel, minus force beam equals 0. And I said force torque in the y direction because this tension is a vector going up. We can break it up into two components. Just like any vector, you can break it up into components. Usually, traditionally, x and y. Force tension in the x direction, force tension in the y direction. So the y is where we're going to hopefully get some useful information out. So I just wrote that out. Then we're going to do the same thing for torques. So a lot of people like torques positive and negative. The only thing I care about with positive and negative is if all the positives are in the same direction until all the negatives are in the same direction. So I really don't look at positive and negative so much as counterclockwise and clockwise. So torque tension is going in the counterclockwise direction, and it's going to be minus torque squirrel minus torque beam. And yes, the minus signs here really don't mean one direction or the other. I think the convention is counterclockwise is positive. I'm not even sure, and I really don't care. Basically, they have different signs because they're in opposite directions. That's all that matters here. So then, looking at the definition of torque, which is a vector, equals radius cross product force. And another way of writing this is torque, which without the vector symbol, is RF sine of theta, where theta is the angle between the two of them. Or you can look at this as R perpendicular F, the proportion of R, the radius, from the pivot, where the radius is perpendicular, or you can look at the other way, where the perpendicular of the force, which is perpendicular to the R. Either way, we'll see what we use. We'll go for it. So let's start with, so we have two equations here. We can start with either one. I'm going to start with forces, just because it doesn't matter. I imagine we're going to have to use both of them. So let's do light blue. So force torque in the y direction. So this is going to be, we can also break it down this direction. These two, breaking the force tension down into up and then over is the same as breaking it down to over and then up. I'm just going to use over and then up because we know what this theta is right here. And there, we can use SOHCAHTOA to find out this side right there. And so that's going to be sine of theta. So sine of theta equals opposite over hypotenuse. Therefore, if we want to find the opposite, that's going to be hypotenuse times sine of theta. And that's supposed to be a y and a p. Handwriting is terrible. I apologize. So we have force tension in the y direction, which is our opposite, is force tension, which is what we want to find, times the sine of theta, okay, minus force squirrel, minus force of the beam. We're given force squirrel and force beam, so that's good. I'm going to set this equal to 0 for now. Yes, I'm good with that. We're going to see where this goes. All right, so now we're going to look at this in terms of torques. So the torques we have here, the torque of the tension. So what we're going to look at this as, we're going to use force tension y, so up this direction, and we're going to use r perpendicular. So we're going to use this formation of it right here. So torque due to the tension is going to be rf sine theta. So we're going to, this is the theta, but I'm going to look at it, actually I'm going to do it this way, r times the perpendicular force. So the perpendicular forces I'm going to use is this one. So the beam is 2.5 meters, and then the component of the force tension that's perpendicular to this beam, this moment arm, is force tension y. And we know that force tension y, I'll call this r beam just to maintain the formality here, that is going to be r sine theta. Force tension times sine theta. There we go. Just like we found it over here to the right. Over here. Oop, I'll underline that real quick just so I know that. Alright, so now, great. We want to find the torque squirrel. Torque due to the squirrel. So this is just going to be r times f. So the force of the squirrel is down. The moment arm is to the right. They're already perpendicular. So the theta in this case is 90 degrees. Sine of theta is sine of 90, which is 1. So I'm just going to ignore that. And so it's just going to be r times f. And the force of the squirrel, they said squirrel force is 2.5 Newton squirrel. So that's 2.5 times its distance, when they said was 0.5 meters from the wall. So 0.5 torque beam. Now for a beam, you can look at the center of mass as in the middle, and that's what we're going to use. So the weight of the beam is 15 newtons, and it's uniform. So the force is going to be 15, and I'm going to use 1.25 as the moment arm, because some of the beam is to the left, some of it's to the right. In the middle, you can say is the moment arm. It's just the average of the two sides. That works with beams. If it was a funny shape, then we'd have to do something else, but since it's a uniform beam, we can do that. Okay, so now we can put this all together, put all the torques together. Ft, that's supposed to be a T, sine of 55 degrees. So torque tension equals, and I'm basically just going to take the negatives, put them over the other side since it equals 0. Another way of thinking, instead of thinking of everything that adds up to 0, you can also think of it as all the clockwises equal all the counterclockwises. Both are completely legitimate. 2.5 times 5 plus 1.25 times 15, and this is the torque of the tension, and that's going to be 2.5 times the sine of 55 degrees times force tension. Do I already have everything? Do I even need to use the forces? I might not. Anyway, we're going to solve this because we can just solve this right now. Go over to Wolfram. So we have quantity 2.5 times 5 plus 1.25 times 15. 15 seems big. Is that the force of the beam? Yep, it is. 2.5 times 0.5. There we go. Divided by quantity 2.5 times sine of 55 degrees. And this should give us the force of the tension. Look at here, and we get, let's see here, 2.5, 0.55, 9.766. Yeah, seems reasonable. I'll believe that. So, force tension. Yes. Force tension equals 9.766 newtons. Whoop. Move that over here. So now we want to find the magnitude and direction of the net force exerted on the hinge joint. Okay. So now, how are we going to do this part? So this part we're probably going to use what we had over here. So let's look at this in terms of x. So I wrote out the sum of all forces in the y direction, which is totally true. But I might want to look at it in terms of the x direction as well. So force, sum of all forces in the x direction, since it's the system, the beam, the squirrel, and such, it's not moving, it's in equilibrium, it's equal to 0. So all the forces to the left will equal all the forces to the right. So we have this force tension going this way, which means we have the force tension x to the left, which means we have a force tension to the right as well. Yep, I'm good with that. And so we know force tension equals, we just found that out, 9.766. So force, so it's going to be SOHCAHTOA. So force tension X is 9.766 times cosine of 55 degrees. Putting that into Wolfram, 9.766 times cosine 55 degrees. We should get a number that's less than 9.766. And we get about 5.6. 5.6 newtons, which is the force tension in the x direction. And since that's the only force in the x direction, that's going to also be on the pivot as well. And then they want us to find the magnitude and direction of the net force exerted on the hinge joint. Okay. So now, one thing I forgot when I drew this, I'm going to draw force, I call this hinge, in the y direction. So I drew the force squirrel, force beam, and force tension to the force tension, but there's also going to be some force up and down on the beam as well. And that's not going to play into the torques, because torque is radius times force, but if the force is at the pivot point, then the radius is 0 and it doesn't add to the torques. So drawing this in now does not invalidate our previous torque calculations. So going over here, adding in the force hinge in the y direction that I should have had earlier, but it's 0. I'm going to assume it's up, so if I get a negative number, it just means that it was actually down. So I can come down here, get rid of this. Force hinge in the y direction equals force squirrel minus force beam, plus force beam, minus force tension in the y direction. Force squirrel, we know, was 2.5. Force the beam, we know, is 15, because they gave it to us in the problem. And then minus force tension y, which we know is, we found earlier, is going to be force tension, which is 9.766, times the sine of theta, which is 55 degrees. We have all the information we should need for this one. Put it into Wolfram. So we do 2.5 plus 15 minus 9.766 times sine 55 degrees. And we get an answer of just about 9.5. That is surprisingly square. Yeah, I'll go for this. Maybe it is. Maybe it is. And so the force tension, force on the hinge in the up direction is 9.5 newtons. Okay, I'm good at that. So now the last part then is we need to find the magnitude and direction. So that just means we turn our individual x and y components into a triangle. So we have to the left 5.6 and up of 9.5. So when we combine those vectorially, so we do 5.6, we do square root of quantity 5.6 squared plus 9.5 also squared, we get an answer that's a little bit bigger than both of them, which is 11.028 newtons. So that's going to be the magnitude of the force on the hinge. And then to find this angle, we'll call it phi just so it's not theta and gets confusing with my other notation. We're going to do SOHCAHTOA again, except this time we're going to use the TOA part. Tangent of theta, tangent of phi is opposite over adjacent. So phi is just going to be the arctangent of opposite over adjacent, which is 9.5 divided by 5.6. And that gives us about 1. That's in radians. We want it in degrees because radians, I have no intuitive feeling for that, is 59.48 or almost 60 degrees. And so for part C, by the magnitude direction neck force exerted on the hinge joint, 3 significant figures, and so I guess 59.5 is going to be 11.028 or 11.0, I guess, for 3 sig figs. And then the angle is going to be 59.48 degrees. So I know it's pretty messy here. To backtrack, the entire idea here is when you have a pivot arm like this, and it's being held up by tension, but it's in equilibrium, there's 2 things that you know. So if it's not moving, you know the sum of all forces. The sum of all forces is going to be 0. And then similarly, you know the sum of all torques are going to equal 0. Meaning that all the clockwise torques are going to equal all the counterclockwise torques. Just like with sum of all forces, all the ups equal all the downs, all the lefts equal all the rights. Plug in the data you know, do some algebra, solve, and get your answer. So hope that helped. See you next time.